Hi, thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. There are a lot of opportunities to recycle phosphorus from waste streams, including municipal wastewater and manure. And as we'll find out today, there's also a massive opportunity really in recycling phosphorus during biofuel production. According to USDA, the US harvests about 5 billion bushels of corn annually to produce bioethanol, which is roughly a third of our total corn production. Those corn kernels contain phosphorus, which remains in the biofuel production leftovers, which are called distillers' grains. And these grains often become a portion of the feed that animals are provided in animal feeding operations. That feed, of course, gets converted in part to manure. And land application of manure for agriculture is a major source of phosphorus pollution to nearby water bodies, as manure is often overapplied with respect to phosphorus. Today's guest asks, what if we extracted the phosphorus before it reached the animals as feed? His team has published a couple of papers that explore the staggering scale of distiller grain production and the associated big opportunity for developing a circular economy for phosphorus, and then how that opportunity compares to recovery opportunities in municipal wastewater treatment. I'm joined today by Dr. Roland Cusick from the University of Illinois in Urbana-Champaign. Well, Roland, thank you so much for joining us for Phosphorus Science Now. I was hoping you could walk us through your paper.
Yeah, thanks, Matt. Actually, today I'll be talking about two papers which comprise a larger story that we're trying to tell related to both the potential and potential environmental impacts of phosphorus recovery from grain processing infrastructure and contextualizing it based on what we can estimate using plant-wide models for water resource recovery facilities that are treating human waste that are much more regulated. So I've included the QR codes so that you can easily access both of these papers. And first, I would just like to acknowledge my research group here at Illinois. The student that did this great work is Ken Rafato. He's wearing the blue shirt and smiling in the middle. And my collaborators on these two papers. On the first, we worked with Vijay Singh in Ag and Bioengineering and Andrew Marganeau in Crop Sciences to tell this story about comparing these recovery potentials and the potential benefits to the Midwest of extracting phosphorus from centralized infrastructure. And then in the second paper, where we focus on the impacts of extracting P from refineries and their downstream end uses of the distillers grain byproducts to animals, we worked with Becca Munich, who is an affiliate of the SPA, and Gerald Scherson at Minnesota. And I'd also like to just acknowledge our funding source. So these are the outputs of a project that is just wrapping up for the NSF Infuse program, where we were developing modeling tools for agricultural watersheds to look more holistically at nutrient recovery and reuse to achieve reduction goals. So what's important to understand about the work that we're doing is that a lot of phosphorus recovery estimates are based on animal heads or human population estimates. And the reality is that wastewater or manure is managed at a site. And so when we think about the potential for recovery and the economics of recovery, we actually have to think in terms of how would that phosphorus be recovered from a centralized facility. That's where it's going to happen. That's where we would have economies of scale. So the basis of this work are plant-wide models that we've developed to estimate phosphorus recovery as struvite in the form of inorganic phosphate from centralized wastewater after it has been flushed and collected and treated, and recovery of phosphorus from corn processing infrastructure. And so we focused on corn processing infrastructure because it has a direct connection to animal feeding operations. So in this process, corn is fermented to extract ethanol, and then all of those byproducts get aggregated and dried to feed to animals. And so the form of phosphorus that is solubilized and partially fermented, it can be broken into about 50-50 split between organic phosphorus as phytate, which is how phosphorus is stored in grains, and inorganic phosphate. Okay, so when we're recovering it, is it a mixed product? These aren't the same products, but we're going to be focusing on the magnitude of phosphorus in total. And so just to give you a sense of these models, just briefly, so at a wastewater treatment plant, the way that we can effectively recover phosphorus is have a mainline process that is treating and removing the phosphorus with polyphosphate accumulating organisms, and they concentrate and release the phosphorus during solids handling. And then we can direct those phosphorus-rich streams to chemical separation technology, like a struvite reactor. Okay, so we've built models for this and estimate potential for recovery across the nation. And then in collaboration with Vijay Singh, we built biorefinery models for both wet milling operations and dry grind ethanol processes. And so in both of these processes, they use water during the steeping process and fermentation process, and that solubilizes phosphorus. So they have streams that have phosphorus concentration that are orders of magnitude greater than we see in environmental waste streams like wastewater or manure. So really, really great opportunity to effectively extract phosphorus. So when we use these models and the publicly available data for wastewater flows and grind rates, we can estimate the potential for phosphorus recovery at a facility level. And what you can see, we use the EPA ECHO database to estimate phosphorus recovery for all of the permitted facilities in the US if they were to implement EVPR, biological phosphorus removal coupled with chemical phosphorus recovery relative to all of the corn processing facilities in the US. And you can see that the ethanol and wet milling facilities are all really clustered with very high values, whereas the vast majority of wastewater plants are very small. So the potential for recovery is quite small. And then you have this kind of separation into some overlap between the largest wastewater treatment plants in the US and the potential recovery for refineries.
And Roland, just to
yeah.
interrupt for a second. So CBs, can you give us the acronyms here? So
yeah.
RRFs are water resource recovery facilities.
Yeah, so green is always going to, in this paper, going to be a corn biorefinery, okay, and that's CB. And then WRRF is the acronym that environmental engineers are using for waste treatment plants, wastewater treatment plants. So water resource recovery facilities. Yeah, so this little icon represents like a clarifier at a wastewater treatment plant, and then this is a little like centralized corn biorefinery with lots of evaporation taking place. And so this map shows both where these facilities are and the potential magnitude. So that box and whisker was just aggregates, and this is showing magnitude and location. And what you can see is where the magnitude is high for wastewater treatment plants is where people live, and that is disconnected often from where crops live. So in the major cities of the Midwest, we have a lot of potential there, but in terms of biorefineries, those are, situated where crops are grown. So not only would we be recovering quite a bit of phosphorus, we broke this down into the region in which they could be recovered. So this the bluish gray colors are for water resource recovery facilities, and the green are for corn biorefineries. And so you can see in the Midwest region, it is pretty astounding how much phosphorus recovery would be possible from corn biorefineries, and how close they would be to the county in which they could be utilized. And you can compare that to like the Southeast or the Northeast, when the majority of recovery potential and the Southwest is coming from dense human populations. So a lot less grain production and processing in those areas. But if we're considering the Midwest and the Gulf of Mexico, then this seems like a great place to focus on trying to facilitate recovery that could have cascading impacts throughout the region. So to try to expand on this story, now we're transitioning into the second paper where first we've showed how much phosphorus could be recovered, but what would be the impacts of extracting that phosphorus from the byproducts that are fed to animals. So distillers' grains are the economics of their cells are really essential to the bottom line of ethanol production. And what makes these products great is that they're fermented, so the animals actually think they taste good, but they have a lot of bioavailable phosphorus because they've gone through some fermentation. But in a lot of cases, the phosphorus is too high for the animals to digest. And so because they become more concentrated, right? The ethanol plants are taking out the carbon they want. So the relative amount of phosphorus is very high. So especially for ruminant animals like beef and cattle, this can lead to just much higher excretion of phosphorus as distillers' grains are fed. So if we extract that phosphorus from the distillers' grains, then less is going to end up in manure. And so we wanted to estimate where, based on where the corn biorefineries are and where animals are raised and fed, how much of these distillers' grains are being utilized locally within the same state or potentially within the same watershed. The paper we just submitted, we actually focused on watershed specifically, but I'll just speak, this is county level transfers. So we used the Groby optimizer to estimate transfer distance and mass from corn biorefineries to animals. And what we can show in this case are estimates for, if we were to extract phosphorus from corn biorefineries, how much phosphorus reduction we would see just in what is fed to animals relative to the amount of phosphorus embedded in manure that's produced in those states and the amount of phosphorus that humans emit in that state. And you can see the potential reduction is not insignificant relative to both the amount of phosphorus in manure and well in excess of the phosphorus emitted by humans in each of these top 5 states. So what is interesting if you look at watersheds is that you can think of this as, the potential to facilitate the meeting of nutrient reduction strategies by trying to involve corn biorefineries as a central player because they serve as conduits between grain production and then animal feeding, right? So so if we just focused in this paper on one watershed. We have another paper under review currently where we look at all potential watersheds in the Midwest with CAFOs. And so for the North Raccoon watershed region, so again, these are just counties that overlap with this watershed, okay? So this isn't an actual watershed study, but based on the amount of biorefineries in the area and the amount of animals, we can see that reduction is well in excess of what the major wastewater treatment plants are having to reduce from their outflows in the Des Moines Metropolitan Water Reclamation Authority is just undergoing an upgrade and expending millions of dollars to meet these limits. And not that they shouldn't, but it's interesting that this utility is having to undergo all of this scrutiny, whereas the biorefineries and the animal feeding operations are not being regulated in the same way. So if the goal is to actually reduce phosphorus substantially and establish renewable recirculation of these resources, increase use efficiency, then we have to start thinking about how to incentivize centralized grain processing infrastructure in this transition to more sustainable approaches to farming and then grain utilization. So just to wrap up, hopefully I've conveyed just the immense potential for pea recovery from corn ethanol biorefineries relative to what can be recovered from wastewater treatment plants. And I just want to say that we focused on corn biorefineries because that data is publicly available. This is also very true for all of the soy processing plants that are extracting protein, peat processing plants. Any grain that has a lot of phosphorus, if they use water, it will be solubilized and potentially end up in wastewater or in a byproduct that is fed to animals. So all of these centralized processing infrastructure are ripe with opportunity for recovery. And since specifically in the case of corn biorefineries, the byproducts are fed to animals, the potential to impact animal-related pollution from excess manure application, specifically with P, we know that's a real problem since a lot of manure is applied based on N and P is over-applied, that this seems to be a very easy and feasible way to reduce those flows without trying to directly enforce numeric criteria on animal feeding operations. But given the constraints of the Clean Water Act, I think probably a more effective approach would be to incentivize P recovery, to generate new fertilizers to reduce our reliance on imports that is growing and to extend the lifespan of our proven reserves domestically. So that's my last point. I appreciate the opportunity to share this exciting research and happy to answer any questions you have.
Yeah, thanks, Rob. That was great. A couple quick questions for you. When you recover phosphorus from these distillers' grains, is that as phytate, or what is the form? I'm trying to get a sense of sort of its agronomic usefulness, just straight out of the gate versus.
Yeah. Oh, great question. I wish I would have included some slides. So I've been collaborating with crop scientists on this project, and they've been doing some reuse evaluation. So it depends on the process. So a lot of corn biorefineries add an enzyme called phytase to enhance fermentation. And with that addition, there is a lot of phosphorus that is mineralized. The phosphorus comes into the refinery as phytate. But through the addition of phytase, then specifically at dry grind facilities that are producing ethanol, then a large portion of it is mineralized. So when we recover it, it's a mixture of calcium phosphate and calcium phytate. But based on the composition, if we can promote further mineralization, then there is really immense potential for potassium struvite to be recovered, which would lower the cost of adding metals to remove that phosphorus. So that's one of the things that we're looking at. And then what we modeled for wastewater plants is inorganic P recovery as struvite.
Great. And then this is kind of a speculative question, but we're kind of moving towards electrifying our vehicle fleet, and I could see this being a capital expense, something that you think about to build a biorefinery, something you think of a 20-year time horizon. So do you see any risk there of creating stranded assets to deal with this as we transition from fuel to electricity?
Yeah, I think that's a really good point to make, and I hope we get to complete electrification, but I also have living in the Midwest and interacting with these grain refiners and seeing how central the refineries are to the rural economy in these states. It's hard for me to imagine, and as renewable fuel standards keep coming out that include ethanol, it's hard for me to imagine them being completely phased out in the near future. Hopefully they will be. That's a sign of progress. But one thing that I'm really interested in, this is a great entry point to understanding, a question that I had is how can we effectively recover phosphorus and find a way to reduce manure-associated pollution given the constraints of the Clean Water Act. And I kind of found this flow. but yeah, I think that's a really good question. I think currently the economics without incentives, even with the economies of scale of these very high concentrations of grams per liter of phosphorus in these streams relative to 50 to 200 milligrams per liter of phosphorus at wastewater treatment plants, those economies of scale don't overcome just the operating cost of calcium addition relative to the cost of fertilizers. So there has to be some incentive to extract this phosphorus, or the refiners aren't going to do it. So hopefully programs would be in place to make it feasible for that investment. But also I think the capital expenses, what we modeled, were much lower than the wastewater treatment plants normalized to phosphorus, because the concentrations are so high. And over 10 and 20-year estimates, that the costs were really associated with operating costs of chemical addition.
Great. Well, hey, thanks so much again for joining us, and I look forward to your future
My
research.
pleasure.
Yeah.
Yeah, I appreciate it.